Right now, if you take a patient's medical file and, feed it into a top-tier AI, it might totally ace a medical board exam.
Oh, yeah, easily.
Right. But then it will completely fail at diagnosing the actual flesh and blood patient sitting right there in the exam room.
It's actually a huge problem.
Yeah, and the reason why is that artificial intelligence is really built for perfect data. It expects this pristine spreadsheet where every single test result is just neatly filled out.
Exactly.
But if you've ever actually navigated the healthcare system as a patient, real-world hospitals are, well, they're a messy, missing data nightmare.
Yeah, the gap between like $1 million research lab and the chaotic reality of a community clinic is just staggering.
Right.
I mean, in a lab, you have all the time and money in the world, but in a clinic, you have whatever test results the insurance company actually approved.
Which is usually not much. And nowhere is that diagnostic landscape murkier than with Alzheimer's disease. So today, for you listening, we are diving into a groundbreaking research paper outlining a new system. It's called AD-CARE.
Which stands for Alzheimer's Disease Clinical Assessment and Reasoning Agent.
Right. And the mission for our deep dive today is to explore how this specific system doesn't just, read data like a smart textbook. It actually acts like a clinical collaborator.
Yeah, it actively hunts down missing pieces.
Exactly. And diagnoses Alzheimer's from the fragmented data you actually find in local hospitals. So, okay, let's unpack this.
Well, to really grasp what a massive leap AD-CARE represents, we kind of have to look at why existing medical AI just falls apart outside the laboratory.
Right, the underlying issue.
Yeah. The core roadblock is known as the multimodal data problem.
Multimodal, meaning Alzheimer's isn't a disease you just diagnose with like a single quick blood draw.
No, not at all. You need multiple modes of information.
Right.
In a perfect world, a patient comes in and gets a comprehensive multimodal workup. So they receive a structural MRI to look at the physical shape of the brain. They get a PET scan to detect amyloid or tau proteins. They go through a grueling battery of cognitive tests, functional assessments, and extensive genetic biomarker sequencing.
Wow. That is a lot of tests.
It is. And traditional AI models are trained on that exact perfect scenario. They assume all of those inputs are just going to be sitting right there on the desk simultaneously.
But stepping back into reality, a patient at a rural clinic might have, an MRI from 2 years ago, a basic memory test from last week, and absolutely zero genetic or PET scan data.
Because the hospital doesn't even own that equipment.
Exactly.
Yeah, missing modalities are the rule, not the exception. The data is entirely patchwork.
Right.
So when a standard deep learning AI encounters that gaping hole in the file, say, the missing PET scan, it basically panics.
It just doesn't know what to do.
Right. It usually tries to mathematically guess or impute what those missing values should be based on its training.
Which sounds incredibly dangerous. I mean, if I'm a doctor trying to make a life-altering diagnosis, I don't want a black box quietly guessing what my patient's brain proteins look like just to, fill in a spreadsheet.
Oh, absolutely not. It introduces massive biases and hallucinated data. Or, alternatively, the AI just throws an error code and fails entirely.
So, traditional AI is like a chef who can only cook if they are standing in a perfectly stocked Michelin star commercial kitchen.
I like that analogy.
Right. Like if they look in the pantry and they're missing just one ingredient, say the truffle oil they totally freeze, they can't make the dish.
Yeah, they just throw their hands up.
But a real-world doctor doesn't have that luxury. A real-world doctor has to make a meal out of whatever random ingredients are actually sitting in the patient's messy fridge.
That is the perfect way to visualize it. And that rigid requirement for a fully stocked kitchen is exactly why large language models, the tech behind things like ChatGPT, haven't been handed the keys to the neurology department. Until now, they've been limited to answering narrow questions or maybe summarizing text notes. They take whatever data you give them, compress it all together, and just spit out a single feed-forward prediction.
Like a basic output.
Yeah, it's a yes or no with a percentage attached.
So there is no step-by-step reasoning? Like, if it says my patient has an 82% chance of Alzheimer's, I have no idea how it weighed the outdated MRI against the recent memory test.
Exactly. It's totally opaque.
Which brings us to the solution here. Because if the data is inherently messy, the AI itself has to be built to dynamically pivot.
Right.
So how does AD-CARE actually do that?
Well, it uses a modality-agnostic design that's built on an agentic AI framework.
Okay, stop right there because agentic AI gets thrown around a lot lately. What makes this system agentic from a functional standpoint rather than just being, a standard language model?
Good question. So an agentic framework means the AI has a degree of autonomy to orchestrate tasks.
Autonomy, okay.
Yeah, it isn't just generating text. It's executing this four-step loop: observation, thought, action, and aggregation.
I see. So it's less like a magic 8-ball that gives you a single prediction and much more like a general contractor building a house.
Let's follow that contractor analogy, actually. In the first step, observation, the system reads the user's query and looks at the actual data provided.
Okay.
It's the contractor surveying the job site, figuring out what materials were actually delivered that day.
Right. Taking inventory.
Exactly. Then we hit the thought phase. The reasoning engine realizes, hey, I don't have a PET scan for this patient.
And instead of guessing...
Instead of trying to guess the PET scan results, it pivots. It decides to lean heavier on the structural MRI and the cognitive tests that actually are there. So it plans a series of subtasks.
And that triggers the action phase, right? The contractor knows what needs to be evaluated, so it goes out and hires specialized subcontractors to look at specific pieces of evidence.
Yes, the agent actively calls upon specialized tools from its library to process the data it actually possesses. And finally, the aggregation step synthesizes all those separate expert reports into a final, unified clinical assessment.
Okay, I have to challenge this setup, though.
Here.
This contractor analogy sounds great, but adding all these independent subcontractors in separate steps, observation, thought, action, aggregation, doesn't a multi-step AI just multiply the chance of hallucination at each stage?
That's a very valid concern.
Like every time it hands data off, isn't there a risk it completely derails?
That is the exact vulnerability you'd worry about with standard models, which is why the aggregation step in AD care is so tightly controlled.
How so?
It doesn't just summarize freely. The aggregator explicitly aligns the outputs with established clinical guidelines.
Oh, interesting.
Specifically, the National Institute on Aging and Alzheimer's Association criteria. It acts as a strict auditor.
So it's basically checking the work against actual medical rulebooks.
Completely. And the final output is not a black box probability score. It generates a transparent, written report.
What does that look like?
Well, it will explicitly write something like, this patient has normal brain volume, which contradicts an Alzheimer's diagnosis, but the severe cognitive impairment strongly supports it.
Oh, wow. So it actually argues both sides.
Yeah, it highlights conflicting evidence and explains mathematically how it resolved that conflict using those clinical guidelines.
Showing its work. That is absolutely massive for a doctor's trust.
Yeah,
you know?
It really is.
But I want to dig into these subcontractors for a second, because the source material details the specific instruments AD care can deploy. And here's where it gets really interesting.
Yeah, the tools are fascinating.
Right, because it's not just reading doctor's notes, it's actually looking at the physical brain.
Right. The spiralized executors are what give the agent its clinical teeth.
Okay.
When the reasoning engine decides it needs to analyze a patient's brain structure, it hands the raw MRI data over to a set of volume analyzers. And these are built on established neuroimaging software called FSL pipelines.
Okay, FSL pipelines. Break that down for us. What is that pipeline actually doing to an image?
So think of an MRI scan as a massive 3D grid of tiny cubes called voxels.
Voxels, got it.
An FSL pipeline is a specialized software sequence that first computationally strips away the skull from the image.
Whoa.
Yeah, then it segments the remaining brain tissue into gray matter, white matter, and cerebrospinal fluid.
Just separating all the parts out.
Exactly. And finally, it counts those voxels to give incredibly precise volume measurements in cubic millimeters.
And AD care is directing this process to look at very specific regions, right?
Yes. It uses a dedicated tool to isolate the hippocampus.
Because that's tied to memory.
Right. Hippocampal atrophy, the shrinking of that specific memory center, is one of the most reliable early markers of Alzheimer's.
Okay.
If an MRI is in the patient's file, the agent runs this exact quantification to get hard, objective numbers on tissue loss.
That's amazing.
Yep.
And if the patient happens to have genetic testing done, it deploys a different subcontractor called the PHS calculator, right? Or polygenic hazard score.
That's right.
I found the mechanics of this fascinating when I was reading the source, because it doesn't just look at the file and say, oh, you have the APOE4 gene, you're at risk.
No. Biology is rarely that simple.
Right.
The PHS tool takes multiple different genetic variants across your DNA and computes a continuous hazard-based score.
What does that actually mean for the patient?
It essentially plots out a personalized curve, estimating exactly how your risk of developing Alzheimer's accelerates as you age, year by year.
Wait, before we move on to the next tool,
Yeah.
you've got to explain the MRI predictor.
Oh, this is the wildest part.
Yeah, the paper mentions it uses a generative transformer.
Right.
And I know transformers are like the engine behind ChatGPT predicting the next word in a sentence.
Right.
But how on earth does a text prediction engine forecast a physical brain structure?
It's a brilliant application of the technology, actually, because to a machine, an image is just sequential data, just like words in a paragraph.
Oh, I guess that makes sense.
Right. So instead of learning the grammar of English, this generative transformer has learned the grammar of neurodegeneration.
Wow.
By training on thousands of sequential brain scans, it understands how atrophy spreads over time.
So you hand it a current MRI, and it's basically predicting the next pixel of deterioration.
Precisely. It forecasts structural changes 6 to 18 months into the future.
That is wild.
It generates a mathematically probable follow-up MRI to show the doctor exactly what this patient's brain might look like down the road if the current trajectory holds.
That is staggering. So, okay, let me get this straight. The general contractor sends the genetic data to the hazard calculator, the imaging to the FSL volume analyzers, looks at the future predictions from the transformer, audits all of it against strict clinical guidelines, and then hands the doctor one cohesive report.
That is the architecture in a nutshell, yeah.
But, you know, a clever architecture on paper is completely useless if it shatters the moment it encounters a real patient.
Fair point.
So, taking this pristine setup and throwing it into a hospital on a busy Tuesday, how did AD Care actually fare?
Well, the researchers conducted a massive validation. They evaluated ATARE on over 10,300 clinical cases.
10,000, that's a huge sample.
It really is. And importantly, they didn't just use one homogenized demographic.
Right.
They tested it across 6 very diverse cohorts.
Right.
4 of these were large public research data sets, primarily AD&I, which is the Alzheimer's Disease Neuroimaging Initiative, and OASIS.
Right, so those are the fully stocked commercial kitchens, the pristine research data where everyone has been thoroughly tested.
Exactly. So to truly stress test the messy fudge scenario, they also included 2 in-house real-world cohorts directly from Chinese hospitals, specifically Xuanwu Hospital and the 3rd affiliated hospital of Sun Yat-sen University.
So real patients.
Real patients. These data sets represent actual on-the-ground clinical realities. Heavy missing data, different scanning equipment, vast heterogeneity.
Let me stop you. I want the bottom line here.
Sure.
Did adding this entire agentic framework, the contractors, the pipelines, the strict auditing, did it actually result in a better diagnosis than if a doctor just, you know, copy-pasted the patient's file into a baseline large language model like GPT-4?
Resoundingly, yes. Across all that messy data, AD Care achieves an 84.9% overall diagnostic accuracy.
Wow.
Yeah, that translates to relative improvements, ranging from 4.2% to 13.7% over the baseline LLM methods. It ranked first in every single cohort.
Even in the Chinese hospital data sets where the data was super fragmented.
Especially there, when standard models hit that real-world hospital data, their uncertainty skyrocketed and their performance just dropped.
Because they couldn't handle the blanks.
Right, they didn't know how to handle the missing pieces. But AD Care maintained high stable classification.
That's incredible.
It preserved a balanced operating profile, meaning it didn't just overdiagnose Alzheimer's to artificially inflate its accuracy numbers. It proved highly resilient to the exact kind of data doctors deal with every single day.
Okay, so we've established it handles the messiness of hospital paperwork. But what about the inherent messiness of human demographics?
Right.
Because we know for a fact that AI has a brutal history of bias.
It absolutely does.
Like a model trained heavily on one specific population will often completely misdiagnose a different one. So if this is going to be a global tool, how does this AI contractor handle, say, an 85-year-old Black patient versus a 65-year-old Asian patient?
You're touching on one of the most critical failures of modern medical AI. Brain structure, baseline cognitive performance, and disease presentation vary significantly across race and age.
Right.
A model that drops in accuracy by 20% just because the patient is a different ethnicity is a mathematical and clinical failure.
Completely.
The researchers explicitly tested AD Care's fairness across Asian, Black, and white racial groups, as well as distinct age brackets.
And how did it actually fix the bias? Because just telling an AI to be fair doesn't actually work, does it?
No, it works because of how AD Care reasons. Standard AI models guess based on textual patterns in their training data, which often contains historical biases.
Right. Baked-in prejudices.
Exactly. AD Care, however, delegates to those objective biological tools we discussed earlier.
Oh, I see.
Right. An FSL pipeline measuring hippocampal's volume in cubic millimeters doesn't care about the patient's race. It is pure objective math. By grounding its final assessment in these hard, demographic-agnostic measurements rather than just statistical guessing, AD Care substantially reduced performance disparities.
So the reliance on biological tools acts as an anchor against bias.
Exactly. When we measure fairness in these models, we look at the standard deviation, the swing in accuracy between different demographic groups. AD Care decreased the average dispersion of accuracy by up to 68% compared to baseline models.
Wow, 68%, meaning it is highly consistent. It isn't systematically failing your grandmother just because she's over 85 while perfectly diagnosing a 65-year-old.
If we connect this to the bigger picture, it combines high predictive performance with severely reduced demographic disparity, which is an absolute necessity for global deployment.
Yeah, you can't launch it worldwide without that. Let's bring this back to the humans actually using the tool, though.
Yeah.
Because it's one thing to see an 84% accuracy rate on a spreadsheet.
Right.
It's another to see what this does to a stressed-out neurologist. The paper features a reader study, right? Testing actual doctors with and without ATARE's help.
Yes. The goal of medical AI must be to augment physicians, not replace them.
Exactly.
So they took 100 cases and had both junior and senior doctors evaluate them independently.
Okay.
First, they diagnosed the patients unaided, just looking at the messy files. Then they diagnosed them with a structured, transparent report generated by 𝗔𝗐𝗂.
Let me guess, the accuracy went up.
It did, by roughly 6 to 11% across the board.
Nice.
But the efficiency gains were what completely reshaped the clinical workflow. The AI more than halved the doctor's decision time.
Halved it.
Yeah, the median case reading time dropped from 59.1 seconds down to 23.4 seconds.
Oh my God. For you listening, imagine what that actually means for your doctor's visit.
It's huge.
That is 35 seconds per patient where the doctor isn't staring at a computer screen, frantically trying to cross-reference a cognitive score with an old MRI.
Right.
That is time they can actually spend looking you in the eye, explaining the diagnosis.
It drastically reduces cognitive load. But the most striking finding from the reader study was how it impacted the less experienced doctors.
Oh, the junior ones.
Yeah, the Agentic report helped the junior doctors elevate their diagnostic accuracy to match and occasionally exceed the unaided performance of the senior specialists.
Wow. It is an absolute equalizer for clinical expertise.
Truly.
But let's be real about a different kind of equalizer here. The cost.
Yes.
If this system requires a multi-million-dollar server farm to run, the rural community hospitals that actually need that junior doctor boost are never going to get it.
That's the sad reality usually, yeah.
Looking at the source material, the cost difference to run these underlying AI engines is astronomical.
It's the silent killer of medical AI adoption.
Right.
I mean, running 10,000 cases through a massive frontier model like GPT-4o costs over $70 in computing power.
$70, okay.
Meanwhile, highly economical models like Gemini 2.5 Flashlight cost under $3.
Under $3.
Yeah, that is an order of magnitude difference. Most health systems simply cannot afford the continuous API costs or the hardware to host the massive models.
Which means only wealthy hospitals get the good AI. But the researchers didn't just hardwire 𝗔𝗐𝗂 to the $70 model, did they?
No, and this is the brilliance of its backbone-agnostic design.
Backbone-agnostic.
They swapped out the underlying language model, the engine testing 𝗔𝗐𝗂, on 8 different models, from the most expensive down to the absolute cheapest.
And the framework itself, like the contractor logic, the FSL pipelines, the guideline auditing, elevated the cheap models.
Remarkably so. When they took that $2.77 budget model and ran it inside the 𝗔𝗐𝗂 framework, its accuracy jumped by over 10%.
Wow.
The agentic structure stabilized the performance of almost all the tested models into a very tight, clinically acceptable range of around 79 to 80% accuracy.
That's incredible. It's like taking a cheap economy car engine, but dropping it into a perfectly engineered aerodynamic race car chassis.
I love that.
Right. The framework, the aerodynamics, the suspension, it does so much heavy lifting that the engine doesn't have to be a wildly expensive supercar motor to get a fast lap time.
That analogy hits the nail on the head. The true clinical value isn't just raw computational horsepower. It's the step-by-step reasoning, the use of external mathematical tools, and the strict alignment with guidelines.
Yeah.
It proved that resource-limited clinics can deploy top-tier decision support without bankrupting their IT departments.
So what does this all mean for you listening, whether you're a patient, a doctor, or just someone tracking the future of technology?
It's a big shift.
It really is. It means we are witnessing a fundamental shift in how medicine operates. We're moving past the era of AI as just a digital parlor trick.
Exactly.
𝗔𝗐𝗂 proves that artificial intelligence can be a reliable, equitable partner that doesn't demand perfect data, but actively rolls up its sleeves to work with the messy, incomplete realities of your local clinic.
Yeah, it really adapts.
It cuts through the noise, levels the playing field for junior doctors, and buys back the most precious resource in healthcare time. Thanks for joining us on this deep dive today. Stay insanely curious, keep questioning the systems around you, and we'll see you next time.
But before we go, this raises an important question for you to mull over.
Oh, definitely.
We've seen how effectively this modality-agnostic contractor approach navigates the missing data and complexity of Alzheimer's.
Yeah.
But what happens when we unleash this exact same framework on other highly ambiguous conditions?
Oh, wow.
Imagine applying this to rare autoimmune diseases where symptoms overlap for years, or mixed pathology cancers where the data is always fragmented and contradictory.
That would be game-changing.
Right. If an AI agent can reliably reason its way through whatever random breadcrumbs of evidence are left behind in a patient's file, hunting down the truth regardless of missing tests, well, the entire landscape of medical diagnostics isn't just improving. It is about to fundamentally change.